So this next topic is going to be a topic of fatigue. In fatigue, I need you to think about many structures that actually anything that's under motion. In my case, I design airplanes. I want you to think about the airplane. The airplane rarely has a static load. By static load, I mean you apply a load and it stays there at a constant level and does not change. Or if it changes very, very, very small over a long period of time. And but that's not the case. If you have flown before and you have been on an airplane, you have realized that as you're flying, your plane is never completely steady. It's going to go through some vibration, some cyclic loading. Sometimes you feel it, sometimes you don't feel it. But at the end of the day, what happens to the plane, you feel that, and especially if there's a turbulence, there's a lot more cyclic loading, and all the cycles actually affect your plane, your wing of the plane, and the whole structure. You can think about the car, that when you're riding the car and the car is actually going up and down, it hits a bump or something. You can think about the bicycle and many, many structures. Any structure that actually has a motion is going to have some sort of cyclic loading. And we want to design and make sure that our structures are completely safe for that. So given that, let's consider the case for fatigue. And fatigue, it goes under a very simple assumption that every structure has a flaw. Okay, if a structure did not have a flaw in the first place, then we will not have fatigue. Okay, and what you can see, these are some testing machines, some examples of testing machines that we have here, and they have unique purposes. In this case, you can think about this panel that's going up and down, and as this is going up, this is going down, and when this goes up, this goes down. So basically, think about it's actually working a sandwich motion. And there's somewhere there's a flaw, there's a crack. You want to see how that crack actually propagates. In this particular scenario, this is actually a rotating. This is to evaluate what happens in in the case of a torsional fatigue. This can also go up and down as well. So basically, in real life, what you may have is you may have something like this. You may have, loads that actually do this. This is a cyclic motion. So what we do in testing is impossible to model this. We will approximate this with some nice sinusoidal functions that completely, just give me a second. Very beautiful sinusoidal functions, and we replace that by that. And what we do in that type of analysis is now we try to evaluate this, which is in testing is easy to model this. So this is basically respect to time, and this is just stress or load level. So in a nutshell, what we are really trying to do is, give me a minute. So this is what it looks like, and this is what we end up approximating. We're going to end up later talking more about this curve. This curve is nothing else than this is your stress intensity factor. If you remember from your crack propagation for mode 1, remember this will be delta sigma, and then you have that crack. So you plot this respect to your delta A over your delta N, and then this tells you what's the behavior of a fatigue model. Let's go ahead and look at a couple of examples to better understand this. In this case, there is a small crack, and the crack is right here. Not sure if you can appreciate this. You can find this video on YouTube. You can see how the crack is growing. I put my mouse right there so you can appreciate as it grows. So it's right there. Now you can see how the crack has gone from here So now it's over here, and watch it. What's going to happen? Eventually, with time, you can see how it starts growing. And the problem that you're working with is you have this completely fixed in the top, and then you're just going up and down here in the corners, here on the edges. Sorry. So then what eventually is happening is creating a lot of stress right here in the middle, and that stress is completely cycling. That's because of bending, right? So this is a typical 3-point bend test. So it's go up and down, up and down, up and down, until what you're going to realize is, look what happens eventually. Let's fast forward this thing. So it keeps on doing it, you can see how it breaks. And then when it breaks, you stop, you bump. This is another example of fatigue as well. Very similar problem. It's also a 3-point bend test. Note that you can see the crack there. But then it starts vibrating a higher frequency. Is cycling at a higher frequency. But look what it starts happening. You can see eventually it starts breaking, and until it definitely just goes and breaks completely. Okay, so those are the problems that we are trying to solve, and this is heavily based on testing. Okay, so fatigue is heavily based on test data. Without test data, we really will not have any of this. So in real life, as I mentioned just previously, to tell you what we will study in this course and how we're going to start. First, we're going to start with a very beautiful problem that actually looks like this: loss of cyclic loading. Okay, and then we're going to expand that to a more realistic problem that actually may look something like this. You might start something like this, but then the cycles are going to change, and then this is going to change, and you can have different cycles at different scenarios, and we want to see how does that affect. But to do that, let's start with our general idea. That's this case. This is what we call one cycle, and we use the letter n to tell the number of cycles. This is n is equal to 1. When we are working in the case of half a cycle, we are talking about the case in which this actually goes up and then it stops, right? It's only one half the cycle. Okay, so this is what we typically, this is what we, more realistic, what we can analyze. And this is how we're going to start the problem. But to do that, we need to define, set straight some definitions.